So far, so good. Looks like I have a few people out there watching. If you can chime in and verify you're hearing me, that would be great. Excellent. Let's see. I don't think I officially put the link into the OneNote, but some people might look for it there, so I suppose I better do that. Live sessions. All right, so actually let me bring this over here. Okay, hello, welcome back, and let's just jump on into it. What I think we're gonna do today, one thing, I thought I created notes when we did this last week, and there was a page of notes, but I haven't been able to find it, like if I put it in a different section or something. But if anybody remembers me making notes and has some idea where I put it and can let me know, that'd be great. But anyway, for now, we have a week 12. I wonder if I created it in the wrong, not in the CSC314 notebook or something. Maybe I had the wrong notebook open. So I have to check my other classes. But what are we going to talk about today? Well, basically, we'll do a stack example program. So that should be, let me zoom this a bit, should be a useful example to help on Lab OX04, if nothing else, and also maybe help understand the stack in general, and you know, it's going to be something a little different, so you'll see some other ideas and tricks and so forth in there in the example we're going to do. So this is going to be read the program, I should say, is going to be read lines of text and print them in reverse order. Okay, a little bit different. Not the individual lines, mind you. We read all the lines of text, so let me kind of add an until until end of file. And just as a reminder, as you may not have picked up on this before, in a Linux terminal, you simulate end of file with a Control D. So, so I don't know, I should probably italicize that because that's not really a part of the description of the program. It's a little tip. All right, there we go. Why don't I just say tip there? There we go. All right, so that's what we're going to do probably for about the first half of this. Then for the second half, what we're going to do is look at, oops, call and return. So this is how you do functions in assembly language. There are Typically we call them subroutines, but you can think of them as functions or methods. And in fact, when we learn how to link in C libraries, we'll actually be using things like standard C functions or C functions that you write yourself and then call from the assembly language, that sort of thing that's coming up. So these are the two things I want to try to get through tonight. We'll see how it goes. And yeah, so let's just jump into it. So first thing is we want to jump into this stack example, and the idea is to just read lines of text until the end of file and then print them in reverse order. So let's think about what that means before we jump into the assembly language. This means we have to save somehow all the lines of text, okay? And now there will be limits on, you know, how much memory you want to use, or and so on and so forth. But as just kind of in general, we want to read as many lines of text as we can. If we hit into memory limits of one form or another, then okay, yeah, the program just won't be able to do what is advertised. But we don't necessarily want to have limitations that are too arbitrary here. We won't be doing memory allocation though, so we will kind of have to define a big buffer of memory that we're going to use, and that will be kind of our limit of the maximum amount of input we can handle. But other than that, we don't want to put a limitation on how many lines or anything. And there are different ways that you could go about this. There's no absolutely one right way, but it is something that kind of naturally uses a stack, because if you'll remember, stacks are last in, first out, or LIFO. Last in, first out. So a stack is actually a very natural kind of thing to use for this kind of reversal problem. We might have used it, you know, back when we reversed the individual characters on a single line, and we did that over and over and over again as an example program way back when. Yeah, that's something that could have used the stack as well. But it was easy enough to just kind of have a pointer walk backwards through the input characters and print them out and then copy them to a new buffer in reverse order. So, but here we have all these lines of text, and we're learning about the stack. So let's see how we can solve this problem using the stack. And there's actually multiple ways you could even go about this in terms of what you push on the stack, because there's two things you could do. You could either have pointers to where each line of text starts in memory and push the pointers onto the stack, or you could push all of the data in the lines of the stack, and that would really kind of be a bad idea. You generally don't want to push large chunks of bulk data like strings and text and stuff like that on a stack. You want integers and pointers and, you know, small data that only takes one word or a double word or a quad word or whatever. Things of that size are usually the kind of thing you want to put on a stack. So pointers take 8, or well, for us, you know, 32-bit machine, pointers take 4 bytes, so that's just a word. So pushing pointers on the stack is fairly natural. Pushing this text onto the stack would be a little bit weird. So we're going to go with the first option, which is we're going to push pointers to these lines of text. Now that does mean we're going to do something a little bit tricky or new or interesting also with how we get our input. And I think you'll find that interesting. In fact, just so you're oriented, let me go ahead and do a bit of a diagram here. I should probably be checking the chat and see if anybody's like asking questions. One thing I'll say, you know, if you do end up typing a question or something into the Discord chat and I don't hear you, don't hesitate to pop over into the voice channel and unmute your mic and say, hey, because I am listening to the Discord voice channel. So that's one way to get my attention. If it seems like I have not looked at the chat screen in a while or something, just let me know. It's actually, you know, for me, it's not in front of me the way it is for you in the screen. It's actually on a different screen, and it can even be behind the window, and you'll still be able to see it in the video. Also, just a quick question out there: do you find having the chat in the video useful? Did it matter to anybody? Like, was it easier? I mean, there weren't a huge number of questions, but I think it's probably better to actually see the question in the chat window if I'm answering somebody's question. So if anybody has any thoughts on whether it's actually useful to have the chat window embedded in the window in the video recording, let me know. Okay, so diagram. What I want to do is just let's think about having a really big buffer. Oh shoot! If this setup, I can't draw with a pen, but I'll make do. I'll just have to draw with a mouse, and it'll be a little sloppy. So let's imagine we have a really big input buffer. Okay. So I'm just going to visualize it as one long strip, and initially we have a pointer to that input buffer right here, okay, right at the beginning, and then some text gets entered. Actually, you know what? I think I'm gonna draw it this way. So let's pretend that's our input buffer, and then I can actually maybe type text into it. There we go. Yeah, so this will be much easier to read. Okay, I think I'll make the text larger though and bold it. And it's always better to use fixed fonts for computer type stuff, I think. All right, there we go. So here's our buffer, and so we have a pointer to the first byte in the buffer, an address of that first byte. And so you could define this buffer the usual way, but you would probably define this really large. We might make this 1,000,000 bytes or something, you know, something substantial. But we start filling it in with sysreads. So so we fill this in with sysreads. And you just fill it in from the beginning, so something, whoops, I lost my font there, something, and then I'll put in a /n to represent return here. So let's say that's what the user types, right? And now what we want to do then is move our pointer over for the next sysread, like so. And so now the user types the next line. So they type something else on that line, and then we move the pointer over. Now for something completely, oops, it wants to wrap it around there. Let me slide this window over there, match our buffer. Now for something completely different. All right, so we're filling in characters into this buffer, and we slide the pointer over. We move the pointer to the next byte to start reading the text in. All right. And you know, that's not that hard to do because we get a count. sysread gives us that count of bytes that it reads in register EAX. So if we just add that to the current pointer, we get the pointer to the first byte of the unused portion of our buffer. All right, so this lets us read multiple lines, fill them into the buffer, and then if we use the stack in a clever way, we can keep track of each line, the address of each line, and the length of each line. We can pop that information off the stack then in reverse order to print all the lines out backwards from that point. So we're basically going to have a loop that just keeps reading in lines of text, moving the pointer, read another line of text, move the pointer, read another line of text, and then we'll have a loop, and also in that loop we're going to push the address and the size of each line onto the stack. So the basic algorithm we're going to do here, we might as well have that. And let me, once again, make the font bigger here so it's readable, and make it bold. So the algorithm we're going to implement here is basically a repeat until end of file situation, and then, oops, where are my bullets? So we're going to repeat until end of file. And what are we going to repeat? Okay, well, we're going to read a line. All right. Push address of line onto the stack. Push length of line onto the stack. And then increase, let's just say it explicitly, let's call it the buffer pointer. Buffer pointer equals buffer pointer plus length of line. All right, so that's basically our input routine. Now we might have a maximum size of the buffer, so we might, you know, to avoid buffer overflow, so to speak, we might want to also have a condition in there that checks and makes sure that we don't have too much input. But let's just get the basics of this down. So once we do that, now we repeat until nothing left on stack, and probably worth putting in question marks here. How do we know when nothing is left on the stack? Would be something to think about, but the basic idea is we're just going to keep popping stuff off. So we pop the let's see, we're pushing the address, so pop a line address, pop a line length, and write that line. Okay, so remember, syswrite needs the address and length of the text it's going to print, right? So I'll just put that as a kind of a tip there. That's really all there is to this, but it will give us an example of using a stack. Plus, we're messing around with addresses a little bit and doing something a little bit different with an input buffer, so that's worth seeing. So now let's go ahead and dive into this. All right. So bringing up virtual machines here, and as usual, it'd be good if you kept up with me. One thing I'm going to announce right now, I kind of decided this a while back, but I didn't ever actually say anything. You may have noticed there haven't been any lecture screenshot drop boxes. So at this point, you're going to get out of these videos what you get out of them to help you do the labs, but I'm not requiring screenshots. But I still would really suggest that you try to keep up with me, do your own examples, or follow along with my example, so you actually create the example I create. You'll remember it a lot better, you'll understand it a lot better if you follow along, even if you have to go back and rewatch and pause and stuff. So I do highly recommend that. But now let's do a new program and dive into it. Okay, so first we want our basically our input loop, and really this is going to use stuff that's similar to what we've done. We need to do a sysread, then we need to check whether we're at the end of file. Let's see how well I can just do this from memory rather than copy and pasting. So we want to move into EDX the maximum size of our buffer. Now that's actually going to be a little different. So I'm going to put that in question marks, because let's go back to what I showed you over here. If we keep moving this pointer to where we're going to start filling in the bytes of the next line of input, then the total size of the buffer that's left over, you fill that in with spaces so I can highlight it. So this is all the unused portion of the buffer. So the amount of space I have in that buffer is going to be less each time. Each time I read in a line, I'm going to have less maximum space that I can read the next line into. So I'm actually going to have to keep track of that. And so each time through my loop for reading a line with a sysread, I need to give it, as the maximum amount of space in my buffer, I need to give it a different number. So so over here, this max size of input decreases with each line. Okay, so we're going to have to think about how that gets calculated and what its initial value is. So we're going to have to, do some stuff here. And actually, I don't even know why I said input loop as a comment. Let's call this the read loop and just create a label for it right there. There's probably some initialization we need to do up here. So we'll figure out what we need to do for initialization as we go. So then let's think about what else we want. Well, ECX, oops, in ECX we want the address. Now, we've always been using a fixed buffer address, but here, again, as we see in the diagram for the idea we're using, we're going to move this pointer over and over and over. So we're also keeping track of that as we go. That has to change each time. So we'll see how we're going to do that. In fact, what I think I'm going to do is use EDI and ESI for that. So let's say move, and let's say ESI will be our address. So I'm just going to call it buffer address, and move EDI remaining buffer. So we're going to use EDI to keep track of how many unused bytes are left in our buffer, and we're going to use use ESI to keep track of the address of the first unused byte. Okay, so that's two things we need to initialize. Now these are going to be defined down below somewhere, so we'll get to that later. But well, actually, let's go ahead and do that now. Why wait? So let's do our. Let's see. We need this in the BSS section because it's not really initialized to anything. So here I'm going to say buffer address is we're going to reserve bytes, and we're going to reserve bytes. Well, we're going to probably want to reserve bytes. Actually, I don't want to call that remaining buffer. Why did I do that? That was a bad name up there. I'll come back up there and fix that. So it's going to be the initial buffer size, not the remaining buffer size. So let me say initial buffer size here. That's what we want to do, not the remaining buffer size. EDI itself is going to keep track of the remaining buffer size. So we're going to reserve some number of bytes. How many bytes? Well, that's going to be the initial buffer size, right? So we're going to reserve initial buffer size. So I need to define what that is. I mean, I could just put a number. I mean, right? And you all know this, but just to refresh your memory. I mean, I could say, okay, well, I want a megabyte, so 1,000,000, right? Whatever. Let's go ahead and make our program a little cleaner. So we'll define symbols here. And I'm going to define initial buffer size as EQU. Let's go, yeah, why not? Let's go 1,000,000. I don't think we're going to fill that up. All right, so, and I should probably, this is one place I should probably go to one of my other programs and cut and paste some of those other symbols that we usually use. So we'll do that in a moment. Let's come back here now. And so with these two things initialized, now we have some idea what we want to put here. So EDX is the maximum amount that we're allowed to read in with a, you know, it's what sysread needs to know the maximum number of bytes to read. So that should be the number of bytes remaining in our buffer, and we're keeping track of that in EDI. And in ECX, we want the address, so we'll put ESI in here. All right. So ESI is going to go up, EDI is going to go down, and that should do it for us, right? Now, then we also have, we need an EBX, we need our code for sysread, which is a 3. This is where it's probably useful to open one of my other programs and just copy and paste my symbols. See, I don't even remember which number is sysread right. I'm pretty sure it's a 3, but now I don't feel sure. So, oh, it doesn't matter which one of these I bring in. There we go. So, yep, it was 3. I was remembering correctly. But at any rate, we might as well have these all defined. I don't know, I might want the space in new line. I'll copy and paste all of it and then get rid of what I don't want. So let's bring these over. And, whoops, wrong program. That's for later. So, there we go. And we're not using that one now, and we're not using this one. So, but we might want to, actually I don't see any reason why this is going to need space or new line defined either. So we'll just go with the basics. So we want a sysread code here. Of course, that could be just a 3, but let's go ahead and use the symbol that's defined. And then let's do move EAX and put the code, whoops, wrong thing in the wrong place. Sysread here, and standard in for standard input there, and of course we need the int interrupt. So Okay, so that takes care of our read, and then we need to make sure that it actually read something, and if it comes back with 0 or negative for its return value of how many bytes it read, and that should show up in register EAX, then we want to get out. So we'll compare, I don't know why I've suddenly started using uppercase for these things. Compare EAX to 0 and JLE less than or equal to I guess we want the right loop. We want to start writing our data out at that point. Oops, no colon for that. So other than that, we want to keep going, except we probably want to keep track of EDI, because when the number of bytes remaining hits 0, we don't want to keep going either. So we might actually just go ahead and do a compare on that as well. So we'll just compare EDI to 0, and same thing, we'll jump to the right loop at that point, and we won't try to read any more data in. And so somewhere down here, we're going to have a right loop label. And probably, let's see, if we get past both of these tests, then we're probably just going to want to jump back up to read loop in order to repeat and read another line. So the only thing I haven't done is updated EDI and ESI here. So we can go ahead and do that pretty easily. ESI we should just add the length of what we read in to ESI, and we should subtract the length of what we read in from EDI. So it's pretty straightforward, and we should probably do that subtraction before we compare EDI to 0. So if it hits 0, we can jump out. So I'm going to do the sub EDI EAX. So subtracting whatever's in EAX from EAI. EAX is just the number of bytes we read in, so we subtract that from EDI. That should give us the number of bytes remaining in our input buffer to be used. And then we can do the compare. We don't want let's see, do we want to add to ESI before we do this comparison? I think, yeah, we probably do. Let's add ESI. Actually, we can probably do, yeah, I think we're safe just doing it like this. There we go. All right, so we're going to add the number of bytes that sysread reads to the address. So that takes care of moving this pointer over for each line read in, and we're subtracting the number of bytes read in from EDI, so that takes care of keeping track of how many unused bytes are left in the buffer. All right, so then we check whether EAX was 0 to indicate an end of file. And if it was, then we jump to a right loop. Then we check EDI to see if we've run out of buffer space. Then it doesn't matter if we're at the end of file. We still want to jump to the right loop because we don't want to overflow our buffer. So either one of these should be fine. Now, you might say, what if EDI goes, could EDI go negative here? And let me just pose that as a question. Figure it out. Is it possible under any normal circumstances for EDI to go negative in this loop? And you have to think about the rules of how sysread works and so forth to come up with that answer. It's a pretty straightforward answer, but it's worth having you guys work that out for yourself. Is it possible for EDI to go below 0? If it did go to below 0, that would mean that we overflowed our buffer, actually, because if you were subtracting the number of bytes you read in, and it was more than the number of bytes that were remaining for those bytes to fit in, you're overflowing your buffer. So so I want you to look at what's going on in these instructions here and see if you can figure out what will happen. Is it possible for EDI? And you need to think about the rules that govern how sysread works to answer that question. All right, so that actually should take care of our read loop, except what have I not done? I haven't pushed anything onto the stack here, have I? Let's see, somebody is answering, yay! EDI shouldn't be able to go negative. You would end up with an overflow, but sysread only reads until the buffer is full. Yeah, so if we're putting in EDI the maximum number of characters we want sysread to read, sysread will never read more characters than that. So EAX, if it reads exactly that many, we will subtract that. We will subtract that number from EDI, and it will be 0 at that point, but it'll never read more than what was in EDI here, because that's the rules of how sysread works. All right, so what we have not done yet is pushed anything onto the stack. The two things we need to push onto the stack are the length and the address. And we need to make sure that we push the right length and the right address. We want to push the length of the line we just read in, and we want to push the address of the first byte of the line we read in. So we want to push the address before the arrow moves, so to speak, here. So if we're here and then we read this line, it's the length of this line we want to push, but we also want to push the address. We want to remember the beginning of this line and how many bytes are in it. Then we want to move the pointer for the next time around. Okay, so that's the sequence we want to do things in. And by the way, one of my little soapbox rants here, not really a rant, but words of advice, you know, when you're trying to write programs, and not just assembly language programs, anytime you can sit down and do diagrams like what I'm doing, it doesn't matter if you do it in a paint program or something like OneNote, and where you can drag this pointer around from place to place, or if you're just doing it with pencil and paper or whatever, you know, always try to, you know, make diagrams to help clarify what's going on and what your program is actually doing. You'll make your life so much easier the more you get in the habit of doing that. All right, so again, the order we want to do things is push the current address, push the length, and then change the address for the next time around the read loop. So, so we want to push the address before we change it. So push ESI is what we want to do there. And then, but we want to push the length. Well, EDI is not the length. EDI is the number of remaining bytes. EAX has the length, so we just want to push that straight up. So there we go. Push address of first byte of current line, and push length of current line. Okay, so those have been pushed on the stacks. We update the address. So that's going to be updated to the first byte of unused bytes in the buffer, and update count of remaining unused bytes in the buffer. Actually, I don't know if count is a good word for that. That sounds like we're going up by 1 each time when we're really going down by chunks. let's call it a tally. We're updating the tally of remaining unused bytes. There we go. All right, so now I think I've got everything I want in that loop. If anybody sees a mistake in my logic, be sure to chime in. I always like to do these on the fly so that you can, if I had it all written out ahead of time, it wouldn't be as natural, the flow of thoughts of how I'm thinking about this, and I think it's important for you to hear that. So I could certainly make mistakes as I'm going kind of on the fly here, so be sure to chime in if you see any issues, or if you're just unclear about why I did anything in that loop. I think actually in some ways this example program, even though it's a new concept with the stack and so forth, in some ways this might be one of the simplest example programs we've done. Now we're ready to, if we've jumped here, we're ready to start writing. So what we need to do is we need to pop the length and pop the address. So again, it's last in, first out, so the last thing that would have gone on was a length. So we need to pop a length first and then pop an address. So basically we want to pop, so we're popping a word off of the stack, or actually a double word off of the stack, 4 bytes off the stack, and we want that to go into, well, actually we want it to go into EDX because that's where sysread expects the size, right? So just pop straight into EDX and we're good to go. Pop the last size from the stack straight into EDX for sysrate. Okay, and then we'll pop the address. So pop ECX, pop the last address from the stack, so far so good. Now let's finish out the syswrite. So we want to move into EBX. What do we want to put there? We want the code for standard out. That's like so. And then we want the code for a sysread, or I mean a syswrite, to go into EAX, and then we actually do the call. So far so good. That takes care of that, and for now let's just throw in an unconditional jump. So it's actually, our output loop is an infinite loop here. We'll think about how to control this loop. I don't think that's too tricky. There's different ways we could do this. I'm going to do it in terms of making sure that we recognizing when we've reached the kind of the bottom of the stack, when we've gotten the stack back to where it started. That's when we want to stop this loop. There's other ways we could do it. We could keep a tally of how many bytes we printed and see if it matches how many we read in. There's lots of different ways we could do it, or we could just look at the address we pop, and when that address equals our original initial address, we could use that as a way of deciding when to stop this loop. But just for the moment, let's just leave it as an infinite loop, because everything else should work here if I haven't made any silly mistakes. And since it's an infinite loop, I can even leave out my exit section. So let's go ahead and save, and we'll call this I guess we'll call it vertical reversal. Since we're reversing, the lines will be reversed vertically instead of the individual lines reversed horizontally. So I think that's a pretty good name for it. Let's see. Did you drop commas in line 33 and 34? Probably. Let's see. 33, 34. Yes, I most certainly did drop my commas. Good catch. All right. Could you save and reopen the file as .asm so the file has index item? Oh, you're right. Wait, why didn't it close? I don't know. So let's close it. All right, now let's try again. Vertical reversal. There we go. I don't know why I didn't do that already, but there you go. Now you have syntax highlighting. And you know, I'm gonna want you to maybe be able to keep up and follow along like in Kdebug and stuff. So I'm actually gonna copy and paste this to the notes. So if you're having trouble keeping up right now, you can just copy and paste. I will say, you know, if you make yourself type this stuff in, you remember it better, you learn it better, and so forth. But at this point, I think you just have to make that judgment call which way to use your time. So let me throw this in here, and I think it generally will copy and paste works better if I give you some lines of comments here at the beginning and the end. So let's do that. All right. So now you have options as far as that goes. Okay, so with this saved, we should be ready to test it out. And let me bump up the, oops. Zoom on this terminal here a bit so it's easier to see. And let's see, NASM -F ELF32. I'm gonna go ahead and do the Kdebug stuff, even though for the moment we'll just run it on the command line, but we're gonna be putting this in Kdebug soon enough. Let's see, vertical reversal, there we go, and let's do the LD-M ELF I386 vertical -O vertical reversal. All right, there we go, and / vertical reversal, and we're ready to go. So as I said, this is going to take input, so something, something, whatever, something else entirely, and now for something completely different. All right, and now I'm going to hit Control D, and wow, something crazy happened, right? So that's because our infinite loop kept going and trying to print stuff that it shouldn't have been printing. But if we scroll back here, we see that we did get our 3 lines there of output that we wanted. So let me just well, now I was going to show you a little tip, but I think it's a sidetrack that we don't need right now. So let's go back, and now let's get rid of that infinite loop. So we're going to want to change that to something other than an unconditional jump. Now we could just do compare ECX, that would be the last address, to our initial buffer address. And just do a jump if greater than back to right loop. That would work fine. No problem with that at all. But let's suppose you were doing something else with the stack and you wanted to make sure you wanted to know you were back to where the stack started, and you didn't have something convenient like this that you could compare to. If you were in that situation, what we could do is we could save the original stack pointer and then compare the current stack pointer to the original, and then we would know that we were done. So that's what I want to do. So up here in our initialization, I want to do one more thing. I want to move ESP, that's our stack pointer. That's just a register. It's a register like the other registers. You don't usually do anything with it directly too much. Well, actually, I shouldn't say that, because actually sometimes you do actually directly manipulate the stack pointer. But for now, we think of it as this thing that push and pop play with. We don't play with it directly. But we do want to save what was in there at the very beginning of our program. So let's go ahead and move ESP, and we'll just have a location. So we'll call this original stack pointer. And so we'll just define a place down here for that. Original stack pointer, and we'll just reserve, we just need 4 bytes for that, so resb4. And that should do that. Then what I can do is compare to this. So I can compare, instead of comparing EX to that, I can compare, and actually let me just leave this as a comment. So this would work fine. Actually, and it would need to go with the JG. But what we're going to do is compare the stack pointer to ESP. And here, we can probably just say jump if not equal to. I think that should be fine. JNE, and jump back to the right loop. So as long as our stack pointer has not gotten back to the beginning, we should be fine. Now, that does mean that we have to be careful about our pushes and pops. Depending on what you do, you could mess with the stack pointer and have it miss its original value and go past it or something. So maybe we would want to say JGE, but actually, if you got to where it was before its original value, you might get a seg fault. I haven't tested that. And if you didn't get a seg fault, you'd definitely be in territory you don't want to be in. So you would want to make sure you've carefully written your program so that after you pop the right number of things, it does get back to its original pointer value. The stack pointer does. So for now, we'll just assume that we have done that correctly. And as long as we're popping 2 words each time through the loop, and we pushed 2 words each time through the loop here, then we can be pretty sure we're eventually going to hit the original stack pointer in the right loop. So this should be fine. And this does give you a way to know when you've gotten back to the beginning of your stack, back to where it originally started, which is something you might need to do for Lab 4 as well. So, and there's definitely other tricks you could do. Like you could maybe, instead of this, you could always push some specific number onto the stack and look for that number. But that's a little tricky, because what if a legitimate piece of data that you pushed on the stack happened to be the number you used as the marker for the beginning of the stack? So that's maybe not really the best idea, but it's at least, out of the box thinking, and it's good to think of different ways to do things. So at any rate, this should keep our loop from being an infinite loop. We find that we're back to the beginning of the stack, but if we're going to do that, we better bring back our exit routine. So let's grab that and copy paste. Like so. And I think that should do it. So let's try that out. If I can get the other window to come up. All right, so rebuilding, reversal. Oh, original stack pointer. Didn't I define that? I thought I defined it. I must have typed it differently. Original stack pointer. Make sure that's spelled the same, and make sure. What was different there? O-R-I-G-I-N-A-L. Oh, that one's spelled correctly. These ones, I left out an I. There we go. Let me put that I in there and there. Okay. That should take care of that. So now it should be defined, and there we go. And now let's do the old LD and run our program again. And here is the first line. I'm not feeling very creative at the moment. Whoops, whoops, whoops. I got a segmentation fault, so I made a mistake. Good, this makes for a good debugging example because I did not make this mistake on purpose, whatever's going on here. I didn't change anything else, did I? My first line is reversed. Yes, you're right. It is. You're talking about line 6? That's exactly right. Good eye, if that's what you meant about my first line is reversed. Yeah, you were right. It was not correct. That's such an easy thing to do because I think all of our instincts want the second parameter to be the destination, and we have to, you know, always make that adjustment. And even I make that mistake. Well, I think the last class we had a mistake that was the exact same problem, didn't we? I say we. I'm the one that made the mistake, but you know what I mean. And that one took me a while to debug, if you'll remember. So yeah, so simple things like that you always got to check for. So yeah, this is our destination where we want to save what the stack pointer originally was. So we want to copy this value to this location, not the other way around. What I ended up doing was trying to change the stack pointer, and it didn't like that. Actually, it probably let me change the pointer, but then the first time I tried to push something onto the stack with the wrong pointer, it was probably pointing to an illegal place to push anything. And that's when it gave the seg fault. So with that fix, I think we should be okay. All right, let's see. First line, second line, third line, fourth line, fifth line, and now for something completely different. All right, and now I'm going to hit Control D to simulate an end of file, and there we go. And now for something completely different. Fifth line, fourth line, third line, second line, first line. So let's come back to the program. So just kind of once again to review, all we're doing is we're reading a line, we're pushing the address of the first byte of the input buffer that we used, and then we're pushing the length so that we can pop those off later and do a syswrite. Then we're incrementing that pointer for the read buffer to the next unused byte in the buffer, and we're decrementing the count of how many bytes we have left in that buffer so we don't overflow it. Checking those things to break out of the loop, and repeating that loop as many times as necessary to read the input. Muppets? No, there's not a Muppets reference in there. Now for something completely different. Is that a line from the Muppets? I thought that was a Monty Python line. Maybe it's both. I do love the Muppets. Watched them religiously as a child. The original run of the series of the original Muppet Show. But so I just dated myself, therefore, if you want to start doing some calculations. And now for... Yeah, definitely Monty Python. Maybe they use it in the Muppets as well at some point. I wouldn't be surprised if Muppets made a Monty Python reference. Yeah. Either one. Both are great. Love them both. Thank you, Tammy. All right. So, let's see. Let's go ahead. Well, let me look at the time. Okay, we've already spent an hour on that. I think I will leave it as an exercise to you guys on your own. Run this in. If you have any doubts about how it's working, run it in KDebug so you can actually see the addresses going on the stack, see the stack pointer value, and so forth. Just to make sure that you're really clear on what's happening. But since we've already used an hour, I think I want to start talking about the new material, because you're going to need that diving into future labs. And so I want you to start getting you ready. Now, hopefully you don't start tuning me out because you're totally worried about just Lab 4 right now. So bear with me a little bit. Or, well, if you really want to work on Lab 4, I guess you can tune me out and then you come back and watch the rest of this video later. So there's options. There's always options. Okay, so what are we going to talk about now? Let me actually bring this over. We're going to talk about call and return, which is, whoops, wrong document. Where is it? Where is it? Where is it? There we go. Here's my quick call and return example. And I think there's not much in this, but I'm just going to go ahead and copy this into the notes as well. And there we go. And there's not much in this program yet. First, I think I actually want to give you some notes on call and return. So as I mentioned in the overview for tonight, call and return are basically the way you do functions in assembly language. And there's going to be more to this that we cover in the next section, but it's basically what makes functions possible, and these things are very related to the stack. In fact, the stack basically exists so you can do functions. That's its real purpose for it being there, sort of with these instructions built right into the microprocessor. Is because it's so important for the ability to have functions. And the essence of call and return, though, is pretty simple. What does call do? It pushes the IP register. Quick, we haven't talked about the IP register much, but do you remember what the IP register is? It's a race. Who can tell me what the IP register is? Okay, I think I've used up the 5-second delay, so you should have heard the question by now. Somebody's maybe got it. Typing, typing, typing. Yes. Well, no, it doesn't hold the... Let's be more specific. It holds the what? It doesn't hold the instructions. It's the location of the instructions. IP register holds address of next instruction to be executed at all times. Okay? As soon as you start executing the current instruction, one of the first things that happens is the IP register gets incremented up to the byte position of the next instruction. Interestingly, just a little side note, put that in italics. As a side note, all jump commands do is change the value in the IP register. So they're not doing anything mysterious at all. They're just changing a number in a register. That's really what a jump command does. Yeah, well, I'm going to continue this side note because it's a little interesting. The regular jump command, you know what? I've never tested this to make sure that I'm not a little bit off base here. So maybe I shouldn't say this without actually testing it, but I'm like 99% sure that this is correct. So if you say jump somewhere, okay, same as, is the same thing as move IP somewhere. Remember, all those labels that you make with colons are really just you're just defining a symbol for an address for that location in your program. So that's just a number. And so you could do move into the IP register some number, and that has the effect of a jump. Let's see. So at any rate, okay, enough of that side note. So the IP address holds, the IP register holds the address of the next instruction. So we push the IP register onto the stack. That's the first thing a call does. And then jumps to the desired address. Let me say that differently. Jumps to the address of the subroutine. And in fact, I might as well do it this way. Let's just say if you do a call and give it an address, so I'm just going to call this subroutine address here. All right. So if you do that, it's going to push the IP register on the stack, and then it's going to jump to the subroutine address. So far, so good. And then what does ret do? Ret, you don't give it any instruction. So ret just pops whatever is at the top of the stack into the IP register. So kind of as a note, this implicitly does a jump there. Okay, so notice when you use the return instruction, it doesn't really know where your last call came from. It doesn't know. The idea is you want to use the return to get back to where the last call came from. But if you had something else on the stack, it would pull that off and it would jump to who knows where. So, and I actually have this in the comments of that sample program as well, but most of the stuff is in the comments there. But it's worth putting in the notes here. Warning! All right. You better clear anything off the stack that you put on it during this subroutine. Because if you had something else on the stack when it tries to do the return, it's going to pop the wrong address into the IP register, and you are not going to get back to where you called it, where the call was made. So, but the idea is, you know, just like, now just think in terms of your C programs or almost any other programming language. If you have a function and you call that function, the function's going to do its thing, and then you come back to where it was called and you pick up right from that point. So in assembly language, that's what call and return are meant for, is so that you can jump to some other place, have some stuff get done for you, and then always get back to where you came from so that you can pick up where you left off. That makes the subroutine code reusable. Whereas if you had to keep track of all that yourself, you'd have to have all kinds of conditional jumps, and it might get very tricky if you had to sort of manually do this. But if you have the call and routine working well together, then you could call that subroutine from many different places. Wherever you call it from, the return gets you back to the last place it was called from. So that's the essence of call and return. It's pretty straightforward. Some of you may say, aha, I get it, and I think I can make use of that based on what Scott has already said at this point, and I can turn off the video and just go get some other work done. And if that's how you feel, that's great, because all we're going to do is just kind of look at some examples and just go a little bit more detail into this. So now let's pop over back to the virtual machine. And so here I've just got kind of the skeleton of a program that's going to do a call and return. Okay, the only thing this program does is call a subroutine called do something, and the only thing do something does is nothing. It just returns. It does nothing and returns. So it's a lying function. It's lying to you. It doesn't do anything. Maybe I should call it do nothing, but I kind of like the fact that it is lying to us. So we call do something and it does nothing and returns. So that's all this program does, and then we hit the exit routine and we get out. So let's just see that in action, and this one we do want to see in KDebug. So I'm gonna make sure this is saved, and then let's do the build and run here. So NASM -elf32-g-f dwarf, and we call return.asm, and then let's do the LD here, -m of 386. And let's see, call return.o-o call return. Okay, so now we can run this thing. Oh, if you run it, it better do nothing because there was nothing to be done. That's good. So now let's see it in KDebug. setting a breakpoint, and let's run. And you know, I copied this over there, so you have it. You can copy and paste it. So do this along with me, even if you have to pause me and lag behind by a couple minutes. You know, because I want to keep you guys, pushing you guys to use Katybug. I don't know if all of you are using it with any regularity yet, but the more you get used to using it, the better, I think. So at any rate, let's click run, and okay, I have too many comments in here, and Katybug does not know where to put the green arrow. Shoot. If I put start in here, hopefully I didn't accidentally, and we interpreted it. Remember, you can actually look at a memory location and interpret as instructions. So yeah, there we have call whatever address, so we're calling to something there. So it is on the correct, the green arrow should be pointing to this line right here, but it's not. So let me exit Katybug and clean some of the comments out of this program for this test. So I'm going to come here, I'm going to do a save as, and we're just dealing with a minor bug in Katybug here that sometimes it just, if you have too many blank lines or comments or something, it doesn't get that green arrow matched up where it should, and I don't want to have the confusion of having it pointing to the wrong place. So I'm going to call this call return clean.asm, and delete the comments here. Let's just delete most of the comments, and probably cleaner than it needs to be, but there we go. And so let's save and see if that doesn't work better in Katybug. So let's oh, why am I rebuilding that? I have to rebuild the one called clean. So there we go. So call return clean.asm. And so let's add clean to these, clean, and clean. All right, so far so good. And now let's do Katybug on call return clean. All right, now let's set that breakpoint again, run, and there, that looks much better. The green arrow is pointing on the actual first instruction in the program, so that is good. And you know, I was just thinking about if you're trying to keep up, and you know, I'm rattling off commands here. Hopefully everybody out there realizes that even though you're watching this live, you can click the control bar at the bottom of the YouTube video screen and jump back a few seconds. So if you didn't know you could do that, or weren't thinking about the fact that you could do that, just keep that in mind. But at any rate, we're ready to do the first instruction. The first instruction is to call do something. So what did I say this does? It's going to push the IP register onto the stack. So let's pay attention to EIP, that's the IP register, ESP, our stack register. Where is it? Let's pay attention to our stack register. And let's put the stack address in there, OXFFFFD1C0, and then I'm going to subtract a bit from it. Let's subtract like 128 bytes from that. Remember, because the stack, if you remember from last time, the stack grows, the address of the stack goes down as it fills up. So I want to have a lower address on the actual stack address so we can see everything that's in the stack. That's what that subtraction is in there for, okay, in my address. And it's kind of nice that it lets us put in a mathematical calculation, so I didn't have to mentally calculate what this is and just put that actual number in there. So now if we can find OXFFFFFC0, all right, so there is the actual top of the stack right now, and what we should see is that the value in EIP should go here where my mouse is, and the stack pointer should then point to that. It should be FFFFD1BC is the address of the first byte of this 4-byte word that my mouse is hovering over right now. And so that's what we should see for that. So let's do a step over and see what happens. And notice the green arrow jumped down to the first instruction inside our do something subroutine. I guess I didn't delete these comments, but they didn't cause a problem. This isn't a totally clean cleaned program, but it seems to tend to be, if I put things at the beginning, kind of right after the start label or something, seems to be where it gets confused on that stuff. But at any rate, it's pointing to the right place here. And if we look at what registers changed, notice ESP and EIP both changed. ESP became FFFF1D1BC. If we look over here, it's got 0804865. And you might recall that that is exactly what was in EIP a moment ago. You can always back up the video by about 2 minutes and see. So you can see that it pushed the value of EIP onto the stack. Now, when we do the return, it's going to pop that number and put that back into EIP. Right now, EIP is pointing to this instruction right here. I mean, the actual address of this instruction is where EIP is pointing. In fact, if we go back to looking at, oops, I thought I had that in there once already. If I go back to address start, which is, this start label is the address of the first byte that comes after it, which is the first byte of this instruction. So start is the beginning of our program. I put that in our memory view. And then actually let's go to the instructions view of that. You can actually, one nice thing, it actually looks at where the EIP is pointing to, and it shows us what the current next instruction is. So if we go back here, you can actually see, yep, start was 8048060. And the next instruction after start would be move EBX, and you can see move EBX here is 8048065. And now let's go back to looking at the memory. And again, recall, that's what we pushed from the instruction register. That's what we pushed to the top of the stack. 8048065, that address. So we have the address on the stack of, and I got to tell you guys, I didn't use KDebug the last time I taught this class. I didn't have a good visual way to show this stuff, students. I'm loving the fact that I can show it to you this way. So we can see here that address pushed onto the stack right there. So you can see very clearly what's going on with call and return, right? So now when we do the return, it's going to pop this number off the stack. So we should see the stack pointer point back to its original top of the stack. And we should see EIP get this number in it. And we should see the green arrow then point to this as the next instruction to be executed, right? So let's do and I'll tell you what, I may have misstated something. I think if you back up, I don't think you'll ever see this address in EIP, because it will only, that address will only be in EIP when this instruction, when that first instruction was executing. So at the time the green arrow was pointing to this line right here, EIP would have been the address of this instruction. But when this instruction starts executing, EIP would point to the next instruction. Okay, so we actually never would have seen this number in EIP. That was a misstatement on my part. But okay, so coming back, we're about to do the return, so let's actually watch it in action. So step, and sure enough, the green arrow comes back to the first instruction after the call. Okay. Yeah, so hopefully that's fairly self-explanatory. Now, this isn't very interesting. You might, something in your gut might say, well, why is this so great? You know, because I could just do a jump. I could just have done a jump to do something and then a jump back to here, right? I could just do jump back to exit since that's where the next instruction is, right? Who's thinking that? Quick poll, is anybody thinking that? It's okay, you're allowed to think that. If that was nagging at you even a little bit, if it was just kind of a vague, you know, you're not really seeing that there's anything better here than just having a jump. So, all right, good. At least one person brave enough to admit that they were thinking that. Great. So, well, here's the thing. Just like functions in C and other programming languages, you can use that function many different places. So here, we can now call this do something subroutine in many different places. Okay? So I'm going to modify, I think we've seen enough in Kdebug right now, so I'm going to get out of Kdebug, modify the program, and show you what I mean. All right, so here we are. Well, what if we wanted to do something more than once? So maybe we just do some random stuff here, move into EAX a 5, and then move into EBX a 10, and then we add EAX, EBX. I don't know why we did that. We just feel like adding 5 plus 10 and getting 15 because we roll that way. And then we want to do something again. Okay? So now can you start to see why this might be a little different than just having a jump? Because if we've done everything, if we're using it correctly, we'll call it here, we'll jump down here, and we'll do something, and then we'll return, and we'll come to this instruction here. And then instruction, and now we want to call it again. So we will jump down here, we'll do something, whatever it is, and then we'll return, and then we will come back to the next instruction, wherever that happens to be. So maybe we have some more stuff. Move ECX 99, decrement ECX, decrement ECX, increment ECX, because we like counting down and then up again, I guess. Okay. Can you mix and match jumps and returns? Technically, you can do anything you want, but you're just going to confuse yourself if you don't always intend for a return to go back to the last time a call was called. That's really the only way you should use call and return. That doesn't stop you from doing really strange things, because you could deliberately push a different address onto the stack or change the return address that's on the stack and then call return and have return take you back to somewhere other than where it was called from. You could do that on purpose. You could easily do that on accident. And you probably, if you do it on accident, you probably certainly don't want to be doing it. You could do it on purpose if you were like deliberately trying to make a really difficult program to understand, maybe to make it harder to hack or something. I don't know. But in general, you don't want to like try to do a jump and then try to use a return to get back where you jumped from, and you don't want to do a call and then later on use a jump to get back to where you called from. Both of those would be a bad idea, because remember, the call puts something on the stack, and then if you just jumped back, you would still have that thing lingering on the stack. Okay? And likewise, a return is going to pop something off the stack, so unless you actually put the address on the stack that you want to return to, presumably with a call, then you're going to be popping something off the stack that's not the address that you wanted to jump back to. So now you can mix jumps and various regular jumps inside a subroutine or inside your main program, but you only want to keep those within the kind of the section of code that you're working with. Excuse me. So, in fact, let's make a loop here. We'll just make it unconditional. Or should I just call this do stuff? So we can have a jump back to do stuff. Maybe we have a conditional jump in here. So we compare ECX to 0 and jump if equal down here. Things like that. So use jumps inside one proper section of code. Okay, so kind of your main program here. Now you could if you wanted to, you could actually have a jump do something, but in general, I would say this is such a bad thing to do that I hesitate even to tell you that you can do it. Okay? So let me make a comment. Really, really bad idea. Also, you could have a label. Let's actually put something to do in our do something function. So let's move some things into a register, EAX. 2, and then move EBX2, and then multiply EBX. So we actually do something there, but let's throw in a label just at a random place. Random label, okay? And let's copy that up here, and we could also jump to that random label. We could JMP random label. Also, really, really bad idea. Okay, you don't want to jump out into the middle of some subroutine and jump back and things like that. That would just you would just end up making a program that was just so complicated. Even if you're the only person working on it, you're gonna get yourself so confused about what's going where and when things are gonna jump, and it's just a bad idea. And likewise, you wouldn't want to throw you know, a jump, you know, maybe it's a conditional jump this time, but so maybe we you know, we do a compare EBX to 5, and then we say jump if not equal to back up there to that skip label. Again, really bad idea. Okay, so those kinds of things, you don't want to mix things up like that. But internal jumps that are jumping around to other locations inside your subroutine, and here start is kind of a subroutine, but it's like main, just like, you know, in C programming, main is a function. It's just a function. Every program has to have a main function, but it's still just a function. It's just the first function that gets called when your program is run. So start is the first thing that gets fired in this assembly language program. And everything from here down to there, that's all part of start. So let me just kind of enclose that with comments. I'm going to put sub in quotes because since it's kind of the main program, it's not really a subroutine if it's the main program, but you kind of get what I mean. It's still a routine, at least. So, and that goes down to here. Okay, and then do something. This is the do something routine. So actually, I'm glad you asked that, because I don't think I would have quite gone into this about how bad it is to you know, kind of mix these jumps up and so forth. So this is the do something subroutine from there down to there. And in fact, you'll notice that at least you're never taught that C has a go-to instruction that could allow you to define, you could actually define labels and a go-to, and that go-to works a lot like a jump. Nobody ever teaches you that you have that. Books rarely mention it. And it's generally considered a bad idea to use it. The whole concept of a jump in higher level programming languages, you have to have them in assembly language programs. It's the only way you can have branching and loops. But in higher level programming languages, they hide the jumps from you. Usually they're called a go-to in higher level languages, but it was quickly realized that go-tos create a lot of headaches, because you go to somewhere and then you go to back to somewhere else, and you go to here and you go to there, and it becomes very difficult to follow the sequence of how things happen in your program. So that's why a language like C has the while loop and the for loop and the do loop and the if else, and everything is structured. So, you know, when you do if, the things that you do when that's true are in those curly brackets, you know, and when you have the else, you have another pair of curly brackets for everything the else does. And when you have a do while or a while, you have curly brackets that expressly delineate the instructions that are going to get repeated by that while loop. Okay, so you don't ever have to have, you don't get to the bottom of a loop and then you don't have to have some conditional, you know, if this is true, jump back to some particular line up above, which is exactly what we're doing here in assembly language, because that's our only way to do a loop in assembly language. But the whole point of newer and newer languages, or one of the points of newer languages, is to make life simpler, but it's also to make code easier for humans to understand and put more of the work of the computer understanding the program on the interpreter or the compiler. So, you know, at assembly language, we're just one step away from the bytes of the machine language. You know, we can bring it up in Katybug and you can just see the bytes of the instructions right there listed in the memory view in Katybug. Like we've done that before. You can see those bytes of the instructions. We're just, you know, in assembly language, we're just one step away from those bytes. And so we have to have go-tos. We call them jumps, but go-tos and jumps are really the same thing. But you know, once you get to higher level languages, even one as, I mean, C is pretty low level as high level languages go, but even there you pretty much don't use a goto. Technically, there is a goto in the C language, but we don't talk about it. Nobody talks about it. Okay? So yeah. So let me see. Where do we want to go? Let me add one more thing. So we've got this stuff that's really, really bad, but I want to kind of push it off to the side now so it's not cluttering up our view. And let's see. Yes, the first rule of GoToClub is we do not talk about GoToClub. The second rule of GoToClub is we do not talk about GoToClub. Perfect, perfect. All right. So let me get these things, these real bad ideas off to the side. And we don't really want this. Well, the random label is not going to hurt anything as long as we don't jump to it. So that, and the skip label, same thing. As long as we don't jump to those labels, we can leave them in there. Hopefully Katybug won't get confused. I want to bring this into Katybug. I want to do one more thing. Let's make another subroutine. So we'll call this one another thing. Actually, and another thing. Now, who can dig up what that's a reference to? And you know, we'll do some things in here. We'll move something into ESI. We'll move whatever's in EDI to ESI, and then we'll increment ESI because it's fun to do that. And then we will we'll call do something from here, and then we'll, I don't know, we'll decrement ESI and increment ESI again, because it's fun to count down by 1 and then count back up by 1, right? Everybody having fun? Are we having fun yet? Are we having fun yet? Okay, so there we go. And then we'll return. And then let's actually call and another thing from our main program somewhere. Let's just throw it in here. Call and another thing. All right, so now we can just think about what's going to happen. So we're going to start our program. We're going to come into here. Maybe we have an instruction. It's kind of silly to have two labels back to back because these two labels will both be labeling the same byte. So let's just throw one more instruction. Let's just throw a move. I don't know, EDX 500 and some big number, whatever. Okay, so we have something going on there. Then we come to the do stuff label, and then we call do something, which jumps us down here. And so we do this and this and this and this, and then we return, which brings us back to where we called it from to the next instruction. So we do that, we do that, then now we call and another thing. So we come down to and another thing, okay? And so we do the instructions in here, and whoa, hey, we call do something. So now we come up here to do something, and we do the instructions in here. We return, which means we come back to where it was called from, and then finish out and another thing. Then we return, we return back to where that was called from, which is up here, and then we continue on, and then we call do something, and then we come in to do something, we start doing these instructions, we hit the return, we go back to where do something was called from, and then we continue on, maybe some of these we would skip or whatever. But at any rate, we finish out the main program and we're done. Okay, so so hopefully that kind of clarifies the importance of call and return. I've called do something here, from here, from here, and even from a different subroutine I call it. And no matter where I call it from, as long as I don't screw up the stack, then wherever I call it from, the return is going to take me back to where it was called from, okay, to exactly where it left off. And just maybe like as a mind blower, possibly a mind blower, we can even put a call, have a subroutine call itself. I can put a call do something right there. Now, there's a possibility that this is, well, who knows what this is, who recognizes what the technical computer science term for a subroutine or a function that calls itself? What's the technical term for that? Recursive, yes. So this would make this, so doing this makes do something recursive. Now, of course, none of this example, none of these, you know, the main program and none of these routines are doing anything worthwhile. This would actually, this is not just recursive, but much like an infinite loop, this would be infinitely recursive because I don't have anything that would break me out of it. So we would come in to do something. The first time we call do something. So if we start from our main program, we call do something here. We come in to do something, we do this instruction, this instruction, this instruction, and then we call do something again. So we come in to do something, we do this instruction, this instruction, this instruction, call do something again. So we come inside, do that instruction, that instruction, that instruction, call do something again. And we just keep doing that. Basically, we keep doing that until we use up all the memory that was reserved for the stack, which is, by default, on a 32-bit Linux system, is normally going to be 8 megabytes for the stack. Usually, you don't use the stack for really huge structures of data. So 8 megabytes is usually enough. Now, that is a limit that you can actually control, and I might as well point that out to you. There's a command called ulimit, and if you use it with the -a option, it tells you of various settings on your system that that have been set, basically, and that you can set to other things. So one of those things is a stack size. And notice it says 8192, and that's in kilobytes, all right? So now, what is interesting about the number 8192? Who can tell me? $8,192 equals what? What kinds of numbers do computer scientists always know? All right, I think that's enough lag. Oh wait, somebody's got it. Okay, we always know binary, and the digits of binary represent what? Analogous to the digits of decimal numbers. The digits of decimals represent what? What do the digits of binary represent? I feel like y'all are on the moon because we've got this 5-second lag. Actually, I think that maybe be Jupiter or Mars or something. Well, bits are the binary digits, but like if you have a 1 in the third binary digit, what does that 1 represent? Just like if you have a 1 in, if you have a 5, say, in the third decimal digit, what does that 5 represent? Four, and 4 is a... With the lag here, I'm not going to let this drag out much longer. See if somebody gets it. I'm going to count it. 4, 3, 2, 1. Nobody's typing it. Power of... 2. 8192 is a power of 2. Specifically, that happens to be 2 to the, let's see, 1024 is 2 to the 10th, so doubled again, so that's 3 more. That's actually 2 to the power of 13. Okay, so, yeah, you should know your powers of 2. Everybody, just memorize your first 20 powers of 2. Actually, memorize the first 16 power of 2, but also know what 2 to the 20th is at least approximately, and 2 to the 30th is at least approximately. Just good things to know. At any rate, so that's 8 megabytes, because that's 8K kilobytes, all right? Because 1K equals, to a computer scientist at least, 1K equals 1024, which is 2 to the 10th, right? So at any rate, the whole point, the upshot of that little sidetrack, that's the stack size. By default, it's 8 megabytes. But you can use this ulimit command. If you Google how to use it, I'll leave that as an exercise to the audience. Find out how you can use the ulimit command to increase the stack size or make the stack size unlimited. Then you can use up all your memory, potentially use up all your memory for the stack. For various reasons, you won't end up being able to quite use all of it, but you can use quite a lot more than 8 megabytes if you want to. So you can change that limit, and then if you run a program with the limit set to something else, then your program can use a lot more memory for the stack. Just a little sidetrack into Unix settings, and there might be something we do, I can't remember. We might run into a situation where we want to play with that, so it's not a bad thing to be aware of. Okay, so let's see, what are we doing on time here? We're close to 10. Who wants to see a walkthrough of this in Katybug, or did y'all feel like the way I explained it pretty well makes it clear? And if you feel like it's reasonably clear what's going on with call and return, we'll be looking at call and return in a lot more detail next time around, so there's plenty more to come about this. But as long as you understand the fundamentals of how these assembly instructions work, just as a foreshadowing, not really foreshadowing, just kind of as a preview of what we're going to be talking about is anytime you have a subroutine, this subroutine, the idea is the subroutine can be called from anywhere. Could you might, if it's recursive, it might be recalling itself. It could be called from other subroutines. It could be called from your main program. It could be called from different places in your main program. And any subroutine is probably going to need to mess around and change registers, right? Well, isn't that going to screw up the thing that called it? Because, you know, if the main program is using EAX for something, and then I call this subroutine, and I come down here, and this subroutine does something with EAX, I've screwed up the main program. It may not have what is supposed to be in EAX. And if the idea is we can call the subroutine anytime we want, then we have to be very careful that the subroutine does not screw up the registers of the routine that called it. But the subroutine is going to need to be able to use registers, and there's no way for the calling subroutine to know what registers the subroutine is going to want to use. So there's really more to making call and return really useful. And the main issue is before you call a subroutine, you probably want to save any registers that you want to keep around, whose values you want to keep around. So you save those registers into memory, then you call the subroutine, and then you restore those registers that you saved. That's one issue that comes up. And the other is, think about actual functions in C programming. Functions like to have parameters. You like to define functions. You give it a parameter so that the function has something to work on, has some information to process. And what we see here, there's no passing parameters. Now, maybe you could do something like we do with sysread and syswrite, where your subroutine is actually set up to use certain registers in certain ways, and you can use registers to pass parameters. But there's actually kind of a better, more standardized way, which is actually the way that C compilers use when they compile your C programs, because every one of your functions in a C program becomes a subroutine, and there is what we call a standard convention for how the calling function saves all of its registers, then passes parameters, and then how the function that gets called, how it gets those parameters, how it restores things when it's finished. You get back to the calling function, how it restores things, cleans things up after the function it called is finished. So there's all kinds of stuff going on there. And there's kind of a very standardized way of doing that. Now, you could write your own assembly language program and do it any way you want to. No rules. But if you want your program to play nice with a C program or with the C libraries, then you have to learn the conventions. And all of those conventions rely very, very, very heavily on the stack. Just like call and return themselves use the stack to keep track of the instruction pointer so it knows where to jump back to when it's time to return. Well, all the parameter passing and everything else also uses the stack. So that's what we have coming up, and we're coming right up on 10 o'clock. So actually, I think this is a pretty good stopping point. Last chance for any questions that anybody has. Maybe you want to ask questions about the lab rather than about the new material, which is fine. We can spend a few minutes on that if people want to do that. Also, don't forget that we have channels over here. We can talk to each other and help each other out with the labs. And remember, since this is text chat, you can ask a question and then, come back an hour later and see if anybody answered. You don't have to have somebody there necessarily at the time. I will try to tune into this every once in a while, but I probably won't be paying close attention until tomorrow evening, when most people will finally be seriously working on this. I know how it goes. But I'll be there because, what? Do I have a life? I don't have a life. At any rate, that's it for tonight, unless people have questions. So fire away if you do. Otherwise, we'll be signing off here. All right, I think there's been enough lag. I don't see that anybody is typing a question. So if you think you have a question, you should just start at least typing random keys into the message box. So I know somebody's typing. Otherwise, I'm going to assume everybody's tired enough and it's late enough that you're ready to wrap up, or you want to focus on other things than this class, which is all good. So I'm going to wait just a few more seconds to see if looks like anybody's typing a question, and if not, I'm gonna wrap it up. All right, I think in 5, 4, 3, 2, 1, signing off. Oh, looky there. I did not start recording locally, so we're going to have to rely on the archive. I hope the archives that YouTube creates work well. I don't think they become immediately available, though. I don't think so, but I think they become available at least by the next day, maybe within less than an hour. So at any rate, yeah, it doesn't look like anybody's asking questions, so we're going to end the stream here.